Good afternoon, everyone. Welcome to the current session. Current session will be from Rafael, Felix, and will be about stealing browser cookies and about how to bypass the newest security measures by Chrome. A few announcements before we begin. We would like to thank you to our diamond sponsors, Adobe and Aikido, and to our gold sponsors, Formal and Dropzone AI. It's there to it's thanks to them that this event is possible, and thanks to the volunteers and donors that this event is happening. With regards to cell phones, please put them on silent mode. These events are streamed, with exception of Sky Talks. And also don't take pictures with everyone in the frame. Be reminded that these talks will be later on published to the YouTube channel. With regards to questions, use the mic so everyone in the stream can hear you later on. And with that, let's get started and enjoy the talk. Thank you.
Hello. Let me just put my mic up here. Hello, guys. So today we'll be talking about stealing browser cookies, bypassing the newest Chrome security measures, which is a very interesting topic for all you red teamers out there that want to get those cookies from the browser. So here we have the content table. You guys, you see about Chromium-based browsers. You guys will see about Gecko-based browsers, WebKit-based browsers, and the future of browser security, which we'll be talking about device-bound session cookies, which is a very nice implementation to make cookie storage more secure. And also, we have a live demo of a proof of concept tool that extracts all of those browsers, cookies, and other data, including saved accounts. So let's get started here. Who am I? I'm an offensive security lead with 6+ years of experience in malware development and analysis. I work at Hakai Offensive Security, which is a Brazilian company focused on red teaming and offensive security. I created Coffee, which is a Rust-based cough loader that leverages beacon object files for ease of use. I did the POC for the CV 2024-21338, which is an admin to kernel Windows driver exploit. And I really like Rust. I really like bypassing EDR protection. I really like Go, Python, and everything that relates to systems programming and bypassing EDR and antiviruses, especially low-level programming. So let's get started with the main issue. The first one is that info stealing malware has been a persistent threat. You've guys seen probably a lot of people getting compromised from those types of malware. Nowadays, it's very, very common to see that happening. Session hijacking through cookie theft is more common than ever. Usually on our operations, we get some cookies from stealers. We have our internal stealer where we can extract sessions and then impersonate with the cookie gathered. Browser vendors are constantly implementing sophisticated security measures. Nowadays, since stealers are way famous than before, browser vendors are implementing more hefty security measures to try to let people not steal this data that easily. Chrome's latest security measures have significantly reduced the effectiveness of traditional attacks, as I've said. So here we'll get to a quick info stealer data analysis. Our team at Chimera, which is our threat intel platform, did a quick analysis. We have a ton of stealer data counting from 2019 to 2024. The key numbers are that 37% year-over-year growth in credential theft, 130 million stolen credentials in 2023, 179 million stolen credentials through October 2024. The geographic leaders are Brazil, India, and those who have a higher population and more digital exposure, which is expected. This research gets into how this data relates to the Human Development Index too, which is very cool. If you guys want to see, after the talk, you can save the link on the QR code. And of course, we have the Steeler families, which Redline gets the dominance here. It's by far the most famous one, and the one that stayed the long on the market. We have SteelC and Luma too. Luma is the newest one. We had a record September 2024 spike with that one. It's getting way famous too. A lot of people are delivering malwares which use the Luma Steeler family. And of course, new variants appear monthly. And yeah. So let's get to Chromium-based browsers. How do they encrypt the data? Here I just wanted to show you guys a little bit of the evolution of Chrome security. From 2015 to 2020, we had the DPAPI integration, which is the data protection API, which Windows provides. So you can encrypt data with a key which is present on your computer. This was implemented till 2020. Then in 2020, from 2023, we have the AS256 GCM encryption of the state key that had the integration of DPAPI. On 2023 till 2024, Chrome implemented a new encryption called AppBound encryption, which means application-bound encryption. So everything that is encrypted gets bound by the application itself, making it more secure. We'll show you guys later on how this works. But basically, you have a service that runs as Entity Authority System. And this service encrypts the data with DPAPI and then re-encrypts it as normal user level. From 2024 to 2025, we have some changes between AS256 GCM to SHA-2 Poly 1305, which is encryption method used especially on blockchain, I think. I don't know why they implemented that one. Maybe because it's more optimized or something like that. But yeah, they changed the key and the algorithm on 2024 to 2025. And in the near future, which is already shipped on the Chrome Dev and Chrome Beta builds, is device-bound session cookies, which we'll show you guys later on on how it works, and also some possible attack vectors, some brainstorming here to see if you guys can get some idea of an attack. So let's start with the foundation of Chrome. We have the location of the cookies on each operating system. I'll be talking about every operating system for every browser. In the case of Gecko, Firefox, the implementation is cross-platform, and Safari, of course, had its version on Windows, but nowadays it only has on macOS. So the main cross-platform here browser will be Chrome. On Windows, we have the local app data folder. At Google, Chrome user data, default for the default profile, or profile and the profile number, /network/cookies. On macOS, we have the home folder, at library, application support, Google, Chrome, default, or the same profile number, /cookies. And on Linux, this folder is usually on .config, /Google, /Chrome, /default, or profile number, /cookies. The database format is SQLite3 with the cookies table containing the host key, the name, and the encrypted value columns where all cookies are. And the master key location, finally, is stored at the Google Chrome user data local state file, which is a JSON file at the OS underline crypt dot encrypted underline key field. So let's get into the application-bound encryption architecture. You guys can see a diagram here straight from the Google website, actually, when they implemented this security measure. But here I have some key points for us attackers on how we can implement to steal from application-bound. So first, you need administration privileges to run. Then we'll need to use SE debug privilege. We'll have to elevate our process privilege to access either the LSASS process or the winlogon process, which allow for some reason for you to duplicate their token and then for you to assign that token to the current process, allowing you to access any the authority system services. So then you need to duplicate the token with the security impersonation level. Then you need to set the current thread token to the impersonated system token, following the system DPAPI decrypt of the AppBound encrypted key using the crypt unprotect data syscall. Everything I'm showing here, you guys can see later on the repository. I'll leave the QR code at the end of the talk. Everything is written in Rust that I really like. And if you guys can want to implement anything showed here, you guys can do it. It's actually a library. It's a crate. So you guys can just import on your project and start stealing cookies. So yeah, we do the decrypt of the AppBound encrypted key. Then the user decrypt of the result from system decrypt. So we first decrypt as system, then we reverse the token to our normal user access, and then we decrypt again as user, because it's a two-step encryption process. So yeah, the process involves two-stage DPAPI decryption. Here's the post-process data function where the magic really happens nowadays. On top of the application bound, Chrome uses this branding specific function, which actually does a lot of encryption behind it. Since Chromium is open source, you guys can see it there, but I don't know if you guys can see. It has a flag called Chrome specific branding, and we can't unfortunately see the contents of that function because it's an internal implemented function. But yeah, this function does all the state key encryption on top of the application bound. So here we'll get to some disassembly. On the Chrome path, you guys will find the elevator service.exe file. On that file, you guys can throw that file on a disassembly and start looking and understanding how it works. So here I have the key initialization function that gets triggered on a class constructor inside the post-process data function. Since we don't have access to the source code, we need to do this disassembly, right? And on the right, we have the key location for the elevation service with the AES key, the short key, and the SHA-SHA-20 poly 1305 key. Both three keys are stored there. I changed the structure, as you guys can see, to the encryption metadata structure, and we have three key types stored there. So all the keys we need to decrypt are there on the disassembly. With those keys, Chrome then calls the encrypt data function, which is inside the post-process data function, that then encrypts the data passed to it. as you guys can see. Here actually is a call on below, get encrypt key handle, which is something new they implemented. Actually, I wrote this talk 2 months ago, and they changed recently, and this talk is updated, so you guys will getting the fresh technique here. So yeah, here we get the global encryption metadata map, which is the keys, and then this function encrypts with those keys. So let's get to the format. State key decryption. So first, when we get this system user decrypted DPAPI key, you guys will have the key blob, which you can parse first with a 4-byte header length, then header data, then 4-byte content length, then the content data, which is the actual state key. So you guys will have to do some programming here to check first the flag type. The flag byte is at the start of the content data after the length fields. So the first byte is going to be the flag, and then we are going to check this flag. Because we have 3 flags, means that Chrome is doing backwards compatibility. So keys that were created on older versions of Chrome will also work on this algorithm here. So first we have flag type 1 that uses a hard-coded AES key with GCM mode, which is the oldest one. Here we get the content data format. We have the 1-byte flag, 12-byte IV, 32-byte ciphertext, and the 16-byte tag. For flag type 2, is using the most recent one, but not the actual most recent one, which is the SHA-SHA-20 poly 1305 key, which follows the same format, 1-byte flags, 12-byte IV, 32-byte ciphertext, and 16-byte tag. Nowadays, Chrome implemented the Crypto Next Generation API, which Windows implemented to be a replacement, I think, for the data protection API. And then Chrome implemented it, since I think they saw it was stable and every computer had it. So yeah, we CNG decrypt the encrypted AES key, which is in the key blob. Then we short process with the hard-coded key. This is actually a difference here. On flag type 1 and 2, we use the hard-coded key to decrypt using an algorithm. Now we are doing a simple short process with the hard-coded key, which is present on that key table I showed you guys before. So yeah, and the same format too of the content data. Then we decrypt, verify the ciphertext tag to get the V20 master key, which is actually the state key we used to do the cookie decryption. Cookies on Chrome are encrypted using AES 256 GCM2. So here I have a diagram, if you guys can understand better here. So first we start with admin privileges, then we enable SC debug privilege. We find a process in which we can duplicate any the authority system token. We then duplicate that token, impersonate it as system, read the local state JSON, extract the key, remove the application bound header because of the start. Actually, this is base 64 encoded, so you need to decode the base 64, then remove the header, right? And then system DPAPI decrypt, and then user DPI decrypt, parse the key blob structure, check the flag type as I showed you guys, and depending on the flag type, we can decrypt it, verify with the key we've gathered on the disassembly, and then finally get the V20 master key. So here we'll get to the cookie format and decryption because cookies are encrypted, and then with this key we've gathered, we can now decrypt the cookie. I've also added a simple diagram there. If you guys like that, it's easier to understand too because there's a lot of things you guys gonna see, especially on Firefox, the encryption is very complicated. So we connected the cookie SQLite database in read-only mode, query for the cookies with the encrypted value. Then the cookie also has a structure. So we have a 3-byte on the start, which defines in which version the cookie was saved. That actually counts as backwards compatibility, since someone can obviously have older cookies when they were saved on older versions of Chrome. So having this check also helps getting the most data possible. So yeah, we have the V20, V11, or V10 versions for older cookies. V20 is, as you can see, the newest one. So then the cookie is followed by a 12-byte IV, a variable ciphertext, and a 16-byte tag as usual. We then create the cipher, AES256GCM. We use the extracted 12-byte IV as nonce for the AES-GCM, decrypt and verify the ciphertext with 16-byte authentication tag, skip the first 32 bytes of decrypted result, which for database versions higher than 24, in case of last year, roughly, the newest ones, the cookies are now followed by the host key on the start. So you have to validate the host key, then skip the 32 bytes to decode the remaining bytes and get the final cookie value. So yeah, I say here, the decrypted payload contains the SHA-256 hash of the domain followed by cookie value. We then repeat the process for every other cookie, as you guys can see on the diagram too. So let's get to macOS. macOS is a bit different. Here we have an encryption passphrase saved on keychain, which makes it a little bit more secure because keychain on macOS actually works. Chrome Safe Storage here is the name of the saved keychain item. We then use a different algorithm now, password-based key derivation function 2, with a fixed salt called salty salt for some reason, and 1,003 iterations to derive the AES-128 key. So we follow the same process. We connected the Chrome's cookies SQLite database with the extracted master key from keychain. To be clear, you have to get the keychain key, then decrypt, decode with base 64, then decrypt with password-based key derivation function 2. So we query the cookies where the encrypted value starts with the same caveat here with the V20, V11, V10 versions. The cookie structure is very similar actually, but the only difference is that on macOS, it doesn't use AES256 GCM. It uses AES128 CBC encrypted data with PKCS7 padding. So we then create the cipher. The IV is actually a fixed IV of 16 space characters, which is 0x20. And then we use the key extracted from the keychain process as the key. We then remove the version prefix, which is the V20, decrypt the ciphertext and remove the PKCS7 padding from the result. And then the same thing for database versions higher than 24. The decrypted payload contains SHA-256 hash of the domain followed by cookie value. We then decode the remaining bytes as UTF-8 to get the final cookie value. And the process repeats for each encrypted cookie in the database. Okay, so on Linux, it's actually quite similar. On Linux, we have an optional choice to use keyring, GNOME keyring or K-wallet under the same name, Chrome Safe Storage, or if no keyring is installed on the system, the passphrase is actually peanuts for some reason too. We then use the PBKey DF2, password-based key derivation function 2, with a fixed salt salty salt, and one iteration this time to derive the key. The same process repeats. The IV for the cipher is 16 space characters, which is 0x20. We then remove the version prefix, decrypt the ciphertext, remove the PKCS7 padding, and follow the same thing here for the database version, which is the SHA-256 hash of the domain. We decode as UTF-8, and then we get the final decrypted cookie, also with the diagram here, if you guys like that. So yeah, what about other Chromium-based browsers? We've talked about Chromium, Google Chrome, Chrome Canary, Chrome Dev, Chrome Beta, everything that relates to Chrome, but not Brave, Microsoft Edge, and those other browsers. Actually, they are even weaker. As post-process data is a branded implementation, only Chrome does this way. Brave and Edge only implements the application-bound encryption, so then we can just get the last 32 bytes of the decrypted result, which is the system user decryption from DPAPI, to get the state key for decryption. And of course, the same cookie decryption. For accounts, you may ask, it's actually the same decryption as the cookies. So thank you. Thank you, Chrome. Here, let's start with the Gecko. The Gecko is a bit, it's a bit hard actually. So let's see how they encrypt browser data. Let's start with the same format, the foundation. Cookie location on Windows, app data, Mozilla Firefox profiles. On Firefox, actually, the profiles folder has a lot of other subdirectories, which are the different profiles, so you can just iterate it using your code more easily. Actually, one trick for Chrome, inside local state file, you actually have an array of all saved profiles that really helps when parsing different profile names. Because the folder has a lot of files. It's not just a profile folder. So on macOS, it's on library, application support, Firefox profiles, profile, the same format. On Linux, .mozilla/firefox/ any profile that is present on that folder. So yeah, cookie storage is in cookies.sqlite, SQLite database with the MOS cookies table. Account storage is in logins.json, which is a bit different. We're not using SQLite now. We're storing the logins at a JSON file with base64 encoded encrypted credentials. The master key data is stored on a file called key4.db as a SQLite database too, with the metadata and network secure service private tables, which is NSS, which is a very old implementation by Firefox. We have no centralized local state file like Chromium browsers, profile-based architecture with individual profile directories. And here's this is stuff. Firefox stores their cookies as plain text. So no encryption applied, only saved login accounts and passwords are encrypted. So yeah, so I actually searched to see if Firefox is trying to implement something for the cookies. Here's someone creating a request for the implementation of DBSC. And here we have Simon saying, the proposal seems sound, but it's not clear that is a good investment of engineering time. So yeah, we have the cookies in plain text for Firefox for now. So yeah, let's get to the encryption overview. Firefox stores the credentials in two main locations, as I've said, key4.db, which contains the encrypted master key, and logins.json containing the encrypted usernames and passwords. The encryption flow is actually following this process. We have the master password, the master key, the individual credential keys, and then the plain text. Each credential is encrypted separately with an unique salt, and 3 different encryption methods are supported. This is done in order to do backwards compatibility too, because first Firefox implemented a really legacy encryption method, and now we have a bit more modern and more secure encryption method. So yeah, let's get to the master key extraction. So we open the key for the DB database. The global salt is present there, and it's used for all derivations. The encrypted validation contains the password check string, so you have to check for that to see if it's valid. Encrypted master key, which is present on the database too, and validation constant that must be equal to the specific value. Validate the database integrity. We then decrypt the validation data, which we check that must contain the password check. Then we check the validation constant that must be equal to key underline len, which is 248, a bunch of zeros, and then 1. I'll show you guys later. So we then extract the final master key, decrypt the master key with the global salt, and then take the first 24 bytes as the final encryption key. So yeah, as I've said, we have 3 encryption schemas. First, actually, we have to parse an ASN1 structure, which is just another binary format to organize data, especially data which relates to encryption and cryptography. So yeah, we have 3 encryption schemas. We have network security services, password-based encryption, which is the legacy triple dash encryption. We have the MetaPBE, password-based encryption, which is the modern AES. And then we have the logging password-based encryption, which is a simple triple dash encryption. I'll get to the MetaPBE for now. If you guys want to see about the NSS and the logging, you guys can see the repository. I'm just not going to talk about them now because I'll take very long here. And those methods are not being used nowadays. It's just there for backwards compatibility. So yeah, here we have the AS256 CBC algorithm. The key derivation is actually password-based key derivation function 2, followed by a HMAC, followed by a SHA-256, sorry, with 100,000 iterations. The key size is 32 bytes, and the IV size is, of course, 16 bytes. Here I have a diagram, if that helps too. The key derivation process for modern PBKeyDF2. We have the base password, which then follows as SHA-1 of the global salt, which is present on key4.tb. We then call PBKDF2, which HMAC, and then SHA-256 with the base password, which is the SHA-1 of the global salt, the entry salt, which is present specifically on the MetaPBE implementation, on the metadata table on the key4.db. 100K iterations, 32 bytes. The IV is constructed separately from the parts of the AS1 structure. Okay, so let's get to the decryption process. We then first read the logins.json, decode the base 64 prediction blobs, get the raw ASN1 structure on the table. We then parse the ASN1 structure, identify the encryption schema, and extract the salt. We then generate the decryption key, applying appropriate key derivation, which for the modern one is the HMAC chain with PBKeyDF2. We then use the global salt with the extracted entry salt from the table. And then we generate the encryption key and IV. Followed by that, we get the decrypt and validate. We apply the block cipher with AS256 CBC in the case of the modern one. We remove the PKCS7 padding, and then we convert the bytes to UTF-8. The result is the plaintext username and password. In this case, Firefox only encrypts the password. The username you guys can see as plaintext. So here I have the whole diagram of the process. If you guys want, I'll be releasing this slide on the GitHub repository. I'll show you guys in the end. And you guys can take a look with more calm. because it's actually very overwhelming. Sorry, it's a bit messed on the below, but it's going to be okay. WebKit-based browsers. How do they encrypt and decrypt browser data? So let's get to the foundation. Cookie location on macOS. Actually, on macOS, some applications implement WebKit too. So you find these cookies on library, HTTP storages, and binary cookies files. That's very interesting actually, because I can see some applications, for example, even PowerPoint that I'm using right now has some cookies there, which is very nice to take a look if you guys want to do something with Microsoft accounts. Just saying. Library containers come Apple Safari, which is a new folder for Safari. Before, Safari didn't run on a container environment. Now it runs, so we have to access this folder. To be very clear, the application has to have full disk access from the TCC permission. So you can just execute it and be happy. Yeah, of course, you're going to do some phishing to make the user accept that the application can have full disk access or exploit TCC, of course. So yeah, data library cookies, cookies.binary cookies file. The cookie storage is in binary cookies file format. Account storage is in keychain, more complex exploitation. Cookies are stored in plain text, no encryption applied. So yeah, it's just a binary format, a fancy format that you can parse and get the cookie data in plain text, no encryption applied. So yeah, we have the magic, which is cook for some reason, maybe because it's cookie, I don't know. Page count, page sizes array. Then per page, we have the start code of 00, 00, 01, 00. We then loop the cookie count, cookie offsets, and the end code is when it gets to 00, 00, 00, 00, 00. Cookie record, 44-byte header plus strings. We have the size of 4, unknown 4, flags 4, and unknown 4. Each content is followed by 4 bytes each. So we have the domain name, path, value, comment offsets, and the end header, of course. The expiry time and the creation time is 8 bytes, and variable strings are new terminated domain name, path, value, and comment. The flags in this case is 0x00 none, 0x01 secure, 0x04 HTTP only, and 0x05 both. The timestamp is a MAC format, so you have to convert for Unix epoch. Here I have the diagram too. We open the cookie binary cookie. We check if the magic is cook. If not, it's not valid. If it is, we get the page count, page sizes, each page, the start, the cookie count, the cookie offsets, the end. Then for each page, for each cookie, we get the 44-byte header, the string offsets. We then extract the strings, clean the nulls, then get the timestamps, convert the time, the size and flags, and then we assemble and we have the plain text cookie. You guys can actually see the code on the repository if that helps too to understand. Myself, especially, I really like to read the code to understand what's happening. And actually on the browser Voyage, which is the tool I'm going to be publishing, uses a crate called Binary Cookies Reader. So you guys can open that crate and see how he implements this parsing. So yeah, let's get to the future of browser security. Unwelcome DBSC here. So here I have a simple diagram showing how the process works. First, the user logins to a page. Chrome then generates a key pair, which is a public and private key. This private key is stored on TPM, which is the Trusted Platform Module chip. When the cookie expires, because it creates a short-lived cookie every time. So when it expires, we get the HTTP 401 unauthorized. Chrome then pauses the request, requests the private key from TPM. It validates the proof of possession of that private key. Then Chrome presents proof to the server. The server validates this proof, and then we get a new short-lived cookie, and then the process goes on forever, which is actually a very fancy implementation here. So yeah, hardware-backed session security, cryptographic key pair associated with user's device, short-lived cookies with automated refresh, and proof of possession required for cookie renewal. This one is actually very important. The user needs to have a computer with that's compatible with TPM. Because nowadays, not all computers actually have a TPM chip, especially laptops, which are more old. So yeah, this only applies for those who have TPM. So yeah, I'll do some brainstorming here of possible attack vectors. First of all, if you guys want to see more information about DBSC and their whole process for implementing, you guys can scan this QR code on the screen. So yeah, let's get to some possible attack vectors. TPM key extraction, which requires possible physical access for the chip, or some sort of administrative access, maybe correlating to the TPM driver modification here, that we modify the TPM kernel driver for Windows, or any other operating system DBSC implements in the future. And then we can maybe get the private key on the TPM. Virtual memory extraction, maybe on the process of Chrome writing this private key to the TPM, maybe we can middleman, I don't know, requires possibly process injection or memory dumping. And of course, a malware during the registration process. If a malware is present during the session registration, it can extract the private key as it's generated, as I've said. So yeah, here's Browser Voyage. You guys can scan the QR code to access the GitHub repository. It's a Rust project implementing everything mentioned on this presentation. It acts as a crate, so you can implement it in your Rust project too. And a tactic, actually this was for DEF CON because I'm going to do a Red Team Village. I'll do a tactic at Red Team Village. If you guys want to be there, I can help you guys more closely on the implementation. So yeah, let's get to some live demo here. I actually have, if you guys can see here, a terminal with Browser Voyage opened. To run the project, we can execute cargo run as release, and then it runs. It looks for all browsers inside my machine. Let me get some here. So yeah, we extracted data from Chrome. No Microsoft Edge installed here. Extracted some cookies from Brave. Extracted some credentials from Safari, some from Firefox, and all of this data is saved to the browser data export folder. Of course, you have a command line interface here. Let me just get here. So yeah, you can set which browsers you want to extract, the content that you want to extract, cookies, credentials, history, or all. In this case, history is not yet implemented, but it's very easy. Even if you guys want to help with the development process, you guys can. The repository is licensed with GNU GPL v3. So if you guys want to implement the history, it's just history SQLite with no encryption at all. The format you want to export, JSON, CSV, or XML. The output, verbose, debug, trace, and of course, help or version. I'll get to the browser data export folder. You guys can see here all the browsers exported. I show you guys the Brave one. Of course, those cookies are not real out cookies. I just installed Brave and opened google.com, and it already saves some cookies here, as you guys can see. And as you guys can see, the browser extracted in this case was Brave, with the default profile, the host, the name, the value, the path, the expiry, and if it's secure. So yeah, that's it. Thank you. If you guys have any questions, I'm here to answer them. Thank you.